starting. All attendees are in listen-only mode.
Good morning, everyone. I'm Woody Cash, SCT Content Knowledge Officer for the Golden Gate Chapter. Welcome to the Golden Gate Chapter webinar, Understanding OTDR Functions and Measurements. Before we get started, I'm going to go over a brief bit of business, our Golden Gate Chapter business. Coming on March 28th, we are promoting SCTE Great Lakes Chapter presents DAA overview, including FDX. So we hope we'll see some of you on that webinar. April 23rd will be our annual Vendors Day. Please note that it is moved to the DoubleTree in Pleasanton at the 580 or near the 580-680 exchange. Also, we have Member of the Year nominations that's open. I will try to put that in the chat. We also have Vendors Day registration out there. So that is on our website if you would like to. If you would like to go there and register. And we have cable games registration up on our website as well. So you can register for that. I will also try to put those last two links in the chat so you can link off of them. Let's see, and in early April, we're working on a cable games presentation for those that are interested in playing cable games. During our Vendors Day, we will have people there or on a webinar that will answer questions. So we will, you probably check your inbox. That should be hitting your inbox soon. So I'd like to talk just a little bit about SCT promotion or promote the SCT for a second. For some of you may not be members, it would be excellent if you would take time to join. There are a few benefits that you will really appreciate. One is just networking and getting to know people that are experts in the industry we're kind of a small business. So the more people you know, the more connections you have, the more you can kind of navigate around our business. And you can also ask industry experts. There's a couple of venues. Obviously, you can attend an event and there'll be industry experts there. But there's also a venue on the National SCT website where you can ask questions and get a response from experts. There's also just a plethora of archive training up there. This session will be there, so you can refer to it later at a later date, or you can let your fellow SCT members know that this is available for them to stream at their at the best time for them. So today's topic: understanding OTDR functions and measurements. OTDRs are likely one of the most used testing devices in the fiber optic network. It is very important we understand settings and how to interpret measurements. To help us develop a better understanding of OTDR functions and measurements, we have Pete Zarrelli of VeEX. We'll also be throwing out some questions, so be ready, pay attention, be ready for those. I'll put those up and you guys will all have a chance to answer. So with that, I'm going to turn it over to Pete. Thank you, Pete, so much for doing this presentation.
Good morning, Woody. Thank you very much. Good morning, everyone out there in SCTE Golden Gate land. I'm sure there's many folks that are on the West Coast, so it's very early there. Appreciate being asked back for an encore performance of understanding OTDR functions and measurements. Before we get going, a little bit about what we're going to cover today. We're going to try to stick with some basics. The presentation that I use is a combination of presentations from several folks at VeEX. Some of them are very new to OTDRs and some of them are very, very seasoned. So some of the stuff can get down into the weeds, and it's not my intention to really spend a lot of time there because we want to really present the basics and hopefully get everybody a little bit more comfortable with using the OTDR. A little bit about myself, really just a very long career in both the telecom and the cable TV industry. With the convergence of both of those industries, I've been lucky enough to work on both sides at times and now span the both of them as we go forward. The company I work for, VeEX, is a equipment manufacturer. We produce portable and also automated test and measurement solutions. So from anything from the field folks using the equipment to head ends to automated monitoring and 24/7 monitoring of the systems. So there's a lot of stuff involved, and I've been lucky to have a lot of different functions over my career. So that makes very, very helpful as far as working with pretty much all of my customers, all the VeEX customers out there, and hopefully been some benefit to them. So we're going to start by talking about what is an OTDR. Basically, it's a tool. OTDR stands for, I lost my screen here. Hang on a sec. There we go. Optical time domain reflectometer. So let's go back here. It's an electronic tool used to characterize fiber optic cables and links used to transport telecommunications, internet, all kinds of fiber-based services. These have been expanded from the basic point-to-point networks to C and DWDM MUX links, and also fiber to the home. Many sorts of flavors of fiber to the home out there. Prior to us kicking this off, I mentioned to Woody and Nadia there that I haven't done this particular presentation in a while, as I've been doing mostly PON-related presentations in both person and online to various industry entities, not limited to cable TV. So the OTDR basically injects light pulses into one end of an optical cable. Okay, the pulses are reflected back, then they're analyzed and measurements are made based on a variety of factors. And we're going to talk about some of those specific factors and kind of point you in the right direction as far as what's good, what's not good, etc. The OTDR will display all the events detected along the length of the fiber optic cable. So these reflections will create what's called events, and these are going to be at specific distances, and that allows us to analyze the cable and determine what's good, what's not good, and if everything is in the place it's supposed to be. These will be discussed in greater detail along the way. Why do we use OTDRs? Well, in the beginning, cable acceptance. If somebody builds a fiber optic link, we want to verify those cables are received in good condition from the vendors, make sure they're without defects, check for damage that can occur during transportation or handling. So when a reel of cable arrives at your warehouse, someone splices some connectors on it and they do OTDR tests. It's very expensive to hang cable in the air, and it's even more expensive to put it in the ground. If you do not follow these steps, you could be in for a little bit of trouble if something is not in very good working condition. The manufacturers these days have very, very good QA practices, but every now and then something gets out there and it becomes a problem. From working with customers over the years, many customers are even doing this same kind of testing on coax cables before they take them off the reels, just to be sure that everything is good. If you have an outage and have to replace a section of cable, you really need to make sure that that cable is in good working condition before you start to hook it up. System verification. So the OTDR trace will confirm that the system meets the specs and the designs for each component. The OTDR will measure the individual components on a fiber link, and we'll talk about some of those components that generate events and make sure that everything meets the standards. Troubleshooting. When something does not work right, we want to use the OTDR to troubleshoot the fiber. Typically, if a customer has trouble, an outage is one thing. If a customer has no light, that's an automatic use of the OTDR. But if the customer's had intermittent problems, the equipment gets changed, lasers get changed, different things get changed at both ends. If the trouble persists, we need to take a look at the fiber. So the OTDR can be used to troubleshoot the fiber, even if it is in working condition. There may be events in there that may be weather or environmentally generated, pushes them over the edge and causes the customer to have problems. So the OTDR trace will produce something called a map or link map of the optical fiber under test. We'll talk about this on and off throughout this presentation. The technicians will use these to identify, locate, and repair these events or components that are out of spec. So it's the best optical tool for finding problems. People who install fibers will also use power meters and light sources to basically get a loss measurement from point A to point B. Documentation. The OTDR will provide documentations to the customers. The traces show system status. The OTDR traces prove the system has no problems upon completion, construction, etc., and handoff. This is also for design verification. Did the optical link get installed and spliced and connected in the manner that it was presented or supposed to by the design? If you're a contractor, your compensation depends on design verification and meeting specs. Very, very important there. For contractors specifically, here's a link I built for you. These are the specs you provided, the design, etc. Here it is. I want to be paid. So, and that's basic working agreements throughout the whole industry. How does the OTDR operate? Just go into some basics here. It really works like an optical radar system. The pulses of light are injected into the fiber, and the travel time of the reflected light is something called Rayleigh scattering, and Fresnel reflections are measured. These are just two of the technical terms of the principles and how the OTDR works. Rayleigh scattering occurs when a light pulse encounters small variations in the glass. This could be materials, dopants like solvents or something that are added, or other impurities. These are small amounts of light to be scattered in all directions. Okay, this was something that will drive attenuation, things like that. These can also reflect back towards the transmitter. That's called backscatter. We want a minimum amount of backscatter. We'll talk about that in a sec. So backscatter, which can be very small, 0.0001%, is used to characterize the fiber's attenuation for loss and distance. And this will be displayed on a downward slope. And we'll see some of that in several pictures coming up in a little bit. Fresnel reflections occur when a pulse encounters an abrupt change in material density. And this is something that contributed by the index of refraction. This is some physical fiber properties. These are caused by connections, breaks, or where an air gap exists, bad connections, etc. Even bends you can put on that too. Reflections that are very large compared to the Rayleigh scattering, the strength of the reflection depends on the amount of change in the index of refraction. Again, this is the physical properties that when that pulse travels down the fiber and there is an abrupt change in that physical property, it will cause a reflection, and that will generate events where the OTDR can measure. So basically what will happen, the OTDR will produce a pulse, it goes out into its transmitter, it hits couplers, etc., out into the fiber under test. There's the same thing on the receive side where that pulse comes back, it's put into a diode, it will be amplified, converted, and then it will be produced onto the screen. So basically you can get out of this as a pulse of light is transmitted, it reflects back when it hits events, and the OTDR will receive those, convert those into visible measurements on the screen. And we'll talk about different types of those visuals. Fiber properties. If you're dealing with distance, and distance is one of your primary reasons for using the OTDR. If you have an event or the end of fiber, a break, etc., the distance is going to be very important because you need to figure out where that particular event occurs if it needs to be addressed. A bad connection or bad reflection and break, etc. So the OTDR will use this index of refraction to best match the settings of the OTDR to the cable under test. Now, we don't always know what's out there, so there are some default settings that you can use to gain a pretty accurate assessment of where these events are. So the OTDR will calculate the fiber length and event distances by measuring the time elapsed between the transmitted light pulse and the reception of the backscatter signal and reflection associated with that pulse. So that signal goes out, it will be reflected, and it comes back, and that elapsed time will allow the OTDR to compute the distance and figure out where that is. So the display distance and time measured by the OTDR directly linked to the refractive index of the fiber. Any changes in the refractive index will influence the computed distance. So basically, the takeaway here is when we know what kind of fibers out there that we're connected to, most OTDRs have a wide range of fibers models that you can select. There are some defaults that you can use if it's unknown. In probably 75, 80% of the cases, we don't know what's out there. Fiber's been out there for years. Unless you're building a new network, power companies, even cable companies, phone companies that are deploying new fiber networks, they know what kind of fiber's out there, so you can definitely accurately match what's in there, provided the OTDR you're using has that as a selection. So it's very important because you want to get the accurate distances. So you don't want to be off, especially if you have something underground. You don't want to be digging in the wrong place. So the refractive index depends on the fiber material, and there's various formulas that go into this. And this is all done in the instrument. There's no formulas or calculations that need to be done by the user. We'll talk about some other instances where you will be doing some addition and subtraction. We'll talk about that when we get into launch reels and different things. So the distance will be calculated by the OTDR on another formula, measure time times the speed of light in a vacuum over the refractive index of the fiber. So there's that refractive index that comes into play as soon as you start the OTDR. It's very important to know the refractive index of the fiber you are measuring. Errors due to this value not being known exactly are usually greater than any inaccuracies within the instrument itself. The OTDR is an industry-wide or an industry standard device, and all of them, no matter what vendor you purchase them from, work pretty much the same. They're all based on index of refraction. All the formulas are the same. So it's very, very common across multiple platforms. It's probably the easiest instrument to pick up vendor A, then use vendor B, then use vendor C, where I found in things like RF meters and telco type test sets, each vendor is vastly different. The OTDR is very, very similar because of some of these properties and the way the machine operates. Events. So I started to mention events before. We're going to talk about some types of basic events and how to interpret them. What causes an event? Anything that causes loss or reflection, except some scattering, will cause an event. Connections, including damages, cracks, breaks, will cause events. Severe bending, that is macro bending, micro bending, that goes beyond the bend radius of the fiber. A lot of these enclosures are getting tighter and tighter because we're putting more and more fibers in there. Used to be you'd look up on a strand and you see, it's a 24, 48 count fiber in there. Now there's 96, 244, they just go on and on and on, and there's a lot of stuff in there. If you subscribe to some of the social media posts on LinkedIn, Facebook, etc., there's a lot of instances where splicers will display their work. Before and after is a really good one. To get networks up and running, a lot of times it's very, very fast and people do what they got to do to get it working. And then down the road, things need to be fixed. And seeing some of these and the appreciation for the work that these guys do, the craftsmanship, is really, really good to see. There's a lot of care out there with almost all of the fiber technicians that are doing pulling the cables and splicing, etc. Passive devices, muxes, splitters, optical taps, these will all have reflective events, only in one direction though. Mechanical or fusion splices. Mechanical splices typically will generate a reflection. A good fusion splice will not. In a lot of cases, a good fusion splice may go undetected. Okay, the OTDRs can all be adjusted for what they consider a splice. If they see a little event that's 0.01 dB, maybe that's a splice. Okay? Very, very little loss there. So a lot of times the fusion splices go undetected, and that's a good thing. You don't typically want them. I can do a fusion splice of 0.01, and those are very, very good. The machines out there to do splicing nowadays, very, very reliable, and makes life much easier for the folks doing the splicing. Event types are divided into two categories. You have reflective events that have reflective properties that contribute to what we call total optical return loss, or ORL, overall return loss. If you folks have been in the RF industry for years, you're dealing with reflections, and that is a way of measuring return loss, how much signal is being reflected back. Non-reflective events, they have no reflective properties and they have a loss value only. The example at the top right of the screen here, you have the little events labeled 1, 2, 3. None of those three are reflective events. They're all loss events. At the end, over to the right, event number 4, there's a little bit of a reflection there. So that's an example of both types of events in the same screen. The OTDR will display both events types in a trace view and also in a table view. A little bit later, we'll talk about map view. Reflective and non-reflective events continued. So the fiber break or the end of fiber. In most cases, a reflection will be displayed at the end of the fiber before the trace drops to the noise floor. Okay? In these two examples down here, there's a very high reflective event in the left-hand trace at the bottom. That's that large spike that shoots straight up. The one over to the right is a non-reflective event at the end of fiber that looks like it has an APC connector on it. So there's virtually no reflection there, and that trace drops straight down. So that's a couple of pretty severe, and my guess is that these were handmade on a test bench or laboratory because they're just too perfect, too much perfect examples. But we're here to learn. Fibers terminating with a UPC connection usually cause a large reflective event, looking at the screen on the bottom left. Fibers terminated with an APC connector will cause a small reflective event or even almost a non-existent one, depending on the polish characteristics and the quality of it. So that's a couple good examples there. We'll talk about the connectors in a little bit as well. Connectors or mechanical splices. In most cases, these reflections will be displayed at any point of a connection where a small air gap exists. PC, polish connections, and universal polish connectors usually cause a large and medium reflection respectively. So there can be all sorts of reflections there, and that's going to vary on the quality of the connection. APC connectors are designed to cause small reflections. In some cases, they can appear as non-reflective events depending on the polish characteristics and the quality. Both loss and reflectance measurements can be performed on both of these. Fusion splices. In almost all cases, a good fusion splice produces no reflection at the point of connection. Very, very good. As I mentioned before, the splicing skills have been better, the machines are better, and a lot of these splices are not even detected. Only a loss measurement can be performed because it has no reflective properties, or it should not have reflective properties. Fusion splices can be nearly invisible depending on the quality of the fiber, the splicer, and the workmanship and cleaving, etc. Also, one thing to take into consideration when you splice two fibers of different manufacturers together, they could be a little bit off and cause a little bit of a reflection indicated by this thing called gainers. Some cases, the splices may show a power increase or gain, which occurs when two fibers with different backscatter coefficients are spliced together. This is very common when companies purchase other companies and the network design and the products used differ a little bit. So when tested in the opposite direction, that gainer will show a loss value. And again, this indicator at the bottom right here may be a manufactured screen, but that does occur in the field. There was a lot of testing that went on years and years ago when smaller companies would get purchased by larger companies, etc., and those different fibers were now combined and spliced together, collapsing hubs, etc. Bending. This is an important one as well. Bends are classified as non-reflective events. Only loss measurement can be performed because they have no reflective properties. Bending comes in two forms, macro bending and micro bending. Macro bending are losses when a fiber is subjected to a significant amount of bending above the critical value of curvature. this is our bend radius. So when reassembling splice enclosures, cabinets, etc., shelves, make sure that those fibers are in a nice spread out arrangement. We don't want to be kinking everything. When folks do splitters out in the pond world and put them together, there's a very quick routine to check every port of that splitter to make sure that the power measurements are all within the same values, to make sure that there's no bending of cables in the background there. Microbending, signal loss associated with lateral stresses along the length of the fiber. Mechanical stresses, when things are pulled, when things are manufactured, these are inherent to the cable itself, and you could potentially see these in your real test before you even hang or bury the fiber. To distinguish bends from fusion splices, the fiber must be tested at a minimum of 2 to 3 wavelengths. The loss at 1310 nanometers is far less pronounced than the loss at longer wavelengths like 1550, 1625, or 1650 nanometers. I have an old launch reel that I take with me when I do OTDR training and things with customers. And if I run a 1310 wavelength through there, I see from event 0, which is the connection point, to the end, 3,306 feet, one clean piece of fiber. If I then run a 1550 through that, I see a little event. So over the years, that box has gotten a little bit beat up. So it's a very good demo as far as dealing with troubleshooting fibers. If you have access to multiple wavelengths, the suggestion is to use them because they all have different characteristics that they will show. The example on the bottom left is a 1310 and a 1550, riding alongside each other in a decent fiber. Okay, there's a little tiny bit of difference there. In the one on the right, there's a much greater difference. There's a larger loss at 1550, and it looks to be a little noisier as well. So that would be fiber that should be investigated. That loss event number 2 at the 1550 nanometer is much more significant than the small event detected at the 1310 nanometer wavelength. Again, if you have fibers that are questionable, you've got a customer that's been having intermittent problems, you want to test that fiber with as many wavelengths as you have available. Echoes. These can also be referred to as ghosts on the fiber trace. Poor optical connections produce large reflections on the OTDR trace. Reflections will echo back and forth on the fiber system and often appear after the end of the fiber. Usually occur at exact duplicate distances of single or multiple reflective events along the link. Echoes will inhibit no loss, but their levels and reflective properties can be detrimental to high-speed optical networks. So the example at the bottom left, in the middle of the screen where that circle is, there's an event, and then where event number 2 is the end of the fiber. The end of the fiber is determined by typically a loss measurement. If the event is greater than X amount of dB attenuation, the OTDR will declare that the end of the fiber. So if you have a really bad connection that the OTDR detects and it's greater than the end of fiber loss setting, the OTDR will declare that the end of the fiber. So in this case, there are some reflections beyond that at looks like similar distances to the events 1 and 2 in that case. But those green arrows that point from the right to the left is where the OTDR thinks the end of the fiber is. And this is very easy to confirm. Most folks doing OTDR traces have access to the plant drawings, design drawings, etc., so they know what the OTDR distance should be. Got a call last night from a contractor out in Minnesota that was trying to shoot some fibers, and they weren't happy with what they were seeing. So they asked for a little bit of help. We joined a Teams call, got them online, and we started doing some OTDR shots. The first thing I asked him, what's the estimated distance of the OTDR? And we were coming off a little bit as far as the distance. And issue number 1 was they were using a 1 kilometer launch reel, and they weren't accounting for that. They weren't including that in their equation. So that was That was one problem. And then we did a couple fibers. Everything was good. They liked the distances, the loss measurements, etc. No echoes, anything like that. Then they went to another one and they got twice as much distance as they were expecting. And they're scratching their heads. They said, is there any potential that somebody looped fiber 1 to fiber 2 at the other end? And they're like, you know what? That's quite possible, and actually turned out to be the case. A lot of times you'll have folks out in the field that want to save a little bit of time, so they build a fiber from point A to point B. If these guys happen to run 4 fibers and they jump 2 of them each to each other, so they, instead of doing 4 OTDR shots, they just did 2, so they didn't have to test all 4 ports. So that was an interesting one, but we were talking about echoes and things like that along with these guys. So just be wary of where the end of fiber is and if it is accurate according to your documentation. The other way, let me go back to that for a sec. Just before I go past this screen, we get a lot of calls from folks that says, hey, my OTDR is not shooting to the end of the fiber. Left side of the screen and moved over to the right. And as it moves to the right, as events are encountered, if there are loss events, the signal will drop down because you're going through things like splitters, muxes, etc., and those will contribute to the overall attenuation of the fiber. So over on the left here, there's a start of fiber span. These green arrows that point from the left to the right are an indicator of the start. And this is just a VeEX picture. I don't know other manufacturers do. I've worked with several other manufacturers that don't even have an indicator for the beginning. And we'll talk about why it's important to have an indicator for the beginning of the fiber in a little bit. But in our world, we have these green arrows that point to the right. And then on the right, the green arrows that point to the left is the end of the fiber. So that's a pretty easy way to take a look at where the beginning and the end is. There's a scale that goes up on the left there. That's the loss scale. So you can kind of get a handle on how much loss is actually taking place at each of these events. The bottom scale is going to be your distance. That's going to be feet, miles, kilometers, etc. There's all sorts of choices that you can put there. So there's the traces there. There are multiple events in here. There's 4 events. There's a number 1, a 2, a 3, and a 4. And then they all have different values and things. But this is just common navigation of an OTDR screen. This environment here, this one trace was done with a 1625 nanometer shot. The pulse width, which we'll talk about in a little bit, was 1000 nanoseconds. And then there's some distance markers on the screen kind of thing. And this one has a plus and a minus to zoom. There's different function keys that allow you to do different things with the trace. And this is just a basic trace that has 4 events. Nothing complicated about this one, but this is just to kind of give an idea of where you start when you get a trace on the screen after you've done a shot. Interpreting these events. So we talked about the start of the fiber. So that beginning event, that's the OTDR test point. Okay. Then this particular one here goes through a splitter. So that event number 1 is a splitter. There's a little key at the top there. And the key at the top here is just a legend. It's not anything to do with the OTDR, just to kind of guide you as to what this trace has in it. Okay, then there's a splice enclosure, event number 2. So there's very little loss there, no reflection. And then event number 3 is another splitter. So you have a steep drop there, straight down, no reflection. Could be in a cabinet, whatever, pedestal mounted, etc. And then the end of the fiber. So this is just a very, very, very basic trace as far as the OTDR goes. Link maps. So until now, we've been talking about this OTDR trace. For many years now, the industry has been moving towards a map environment, block diagram, whatever you want to call it. In the VeEX tools, we have something called vScout, which is the tool that creates this map. Now, this can be a direct one-for-one translation, or you can go into in much more detail. When I say much more detail, it's the machine doing the work, not so much the technician, the operator. So multi-acquisition analysis and macro bend detection. This gets into the fiber a little bit beyond events and loss, etc. Multi-pulse. So we'll talk about the pulse in a little bit. Multiple pulse sizes to optimize the range and resolution. Again, seeing events that may be close together. If you're dealing with PON networks, there are settings to improve the testing and analysis for PON and various measurement parameters, multi-waves, multi-pulses, to produce this, what we call a link map. So this is basically a translation of that SOR trace that we see on the other pages into a map. And overwhelmingly, the feedback from everyone in the field is that this method is much, much more intuitive to the technician. Now, every vendor in the market has done this, and some of them even sell OTDRs that only have a map. You don't even have access to the trace. And new technicians, as they enter the market, are being trained more so on interpreting a link map, which is much, much easier than dealing with an OTDR trace. I myself am an old guy, and for years I resisted, letting myself adapt to the new world, but it is much easier. When you do stuff in the metro world and the access environment, nodes, etc., the traces aren't very complicated. When you start to get into long haul and combining networks and all these interconnects, they get very, very complex. And the map is a great way to get a handle on the makeup of the link. The folks I was dealing with last night were not OTDR experts, but it wasn't their first rodeo. And they loved looking at the map because they had some links. Parts of the link are their own fiber, and some are leased from a dark fiber provider. So they not only measured their network, but their provider's network as well, and they can tell where the handoffs are, etc. So the link map is really much more straightforward because it has labeling for the events and fiber sections. The old events table had that, but they were, to put them on small screens is tough, and this is just a much nicer layout. Simple pass-fail per event with details view. So you can click on any of those events or select any of those events and get the details. So in this particular example, they've touched event number 3, which shows up as a connector at 9,977 feet. Its loss was 0.41, and there was no reflection there. So that's probably going to be an angled connector. The whole link under test, the measurements, length loss, optical return loss, etc., is listed on the bottom there. So if you want a quick summary, this particular length was 34,039 feet. The end-to-end loss was 24.27 dB, and the ORL was 39.9. So overall return loss. There's probably another mention of this in here, but it doesn't help to mention it multiple times because it's very important. If you're a fiber provider for other companies, so the cable industry has done very well with being a provider of fiber for the cellular companies, the AT&T Wireless, Verizon, T-Mobile, etc. And many of those providers require not only a length, a loss, they require an overall return loss measurement. Now, initially, these were typically in the mid to high 20s. In this environment, the higher the better. This is a calculation of the combined reflections of all the events along the link. So a 30 dB measurement is not as good as a 39. So the higher the better. I like to say just like MER. It's the same principle. So this link map, or whatever you want to call it, overtook the SOR trace as an industry standard years ago. Again, it's much easier for the techs to understand, and techs that are familiar with the network makeup really prefer it, because they can see very quickly when things show up that shouldn't be. Somebody spliced in a connector, somebody did this. It's a very good way of dealing with that trace. And we'll go into this more in a little bit. So setting up the OTDR. So some common fiber optic networks, okay, the old point A to point B, point-to-point network. Okay, you have location A, location B. Then you have a MUX network. Okay, C or DWDM MUXes. Okay, many of those out there, deploying more and more every day. Okay, these you need a tunable OTDR. In a CWDM world, you need an OTDR that has various laser sources in it that are able to shoot and match those CWDM wavelengths. In the DWDM world, there's a bit more complexity, and you are dealing with tunable lasers at these points. So these, as you can well imagine, are a little bit more costly than your typical point-to-point single fiber OTDRs. And these networks, these C and DWDM networks, are carrying much more traffic, much higher capacity, so the test tools in turn will be a little bit more expensive. They've come down in cost over the years as manufacturing practices and advancements have taken place, but they're still a little bit costly. And down the bottom, we have an example of a PON network, or fiber to the home, EPON, GPON, XGS-PON, etc. And we talk about something called central splits or cascaded split environments. Okay, those you don't want to test from the head end downstream. You can, if there's an outage or something, you certainly can do that. But in an environment where it's in service, you want to shoot from the customer end or the field end back towards the head end, okay, to get through the splitters. Also with these, we will use wavelength 1625 or 1650 nanometers, because a lot of times these networks are in service while you are shooting them. Okay, so you can go what they call over the top and use one of those out of service wavelengths to not disrupt any traffic. Some folks will prefer to use 1650 just because it gives them a bit more isolation from active traffic. There's some folks out there that stand by, the further you are away from the traffic, the less interruption you'll have and the less potential for an inaccurate OTDR trace. I don't know how viable that is. We've had customers say 1625 is fine, 1650 is fine, doesn't really matter. But in any of these environments, you need to make sure that you're testing from the proper location. So location A and B at the top, you can use any wavelength if you're on a dark fiber. If you have traffic there, you want to use 1625 or 1650. In the tunables and the C or DWDM, you want to select a specific wavelength that has no traffic on it, or you don't want to disrupt any of the traffic that's there. So you want to make sure that you get the right wavelength traffic-wise. And also, the MUXes will act like filters. So if I pick the wrong wavelength, I may try my shot from the customer premise, and I say, hey, I'm only getting to the MUX. That distance indicates where the MUX is. So you need to make sure that you're on the right channel or wavelength. Okay, this is a good way to verify if splicing is correct. As you go up in MUX capability, more channels, you have more splicing that needs to be required and more of a chance for mistakes. Choosing the proper tools. Very basic OTDRs, your typical 1310, 1550 nanometer wavelengths. These are lower cost. You can outfit more techs. They're easy to get up and running. Basically, they will address no light situations. Tech goes out to a customer premise, these out of service, no light. Slap your OTDR on there, run a 1310 or 1550, and figure out where the end of the fiber is. So very simple, very easy to use. Tunable, so the WDM environment, C and DWDM wavelengths, like I said before, these are a bit more complex or a little bit more of a cost and they're based on the ITU grid, and they're also channelized. And these are required to deal with MUX networks. Okay, if you use a standard OTDR, that's going to hit a MUX, it's going to stop there. And some companies that have maintenance folks out in the field, this is perfectly fine because they're only dealing with outages. Where a construction environment, somebody building a C or DWDM channel out to a customer, they want to prove that channel out all the way back from the customer premise through the MUXes over to the head end to make sure that their circuit is good. So they need a tunable to address test and turn up in those networks. And also PON optimized for fiber to the home networks, fiber to the X networks. Okay, these are going to be configured to have profiles that accommodate for splitters and taps because it's a different network topology having those splitters and things out there. In an environment where you're doing test and turn up where there's no live traffic, perfectly fine to use any of those other wavelengths. If you're doing any in-service testing, okay, you're shooting alongside live customers, you're going to want to use 1625 or 1650 nanometers to shoot over the top and not disrupt any traffic. If you have a customer on a street that's out, he's got no light, but you have other customers off of that same splitter, they're in service, you don't want to disrupt them, you use 1625 or 1650 to deal with that particular customer's issue. He may have a drop that got cut somewhere or a connection has gone bad at their splitter connection. Common portable OTDRs have three main test modes. Okay, easy OTDR is a full auto mode. Okay, this is your novice user, your outage. We just want to hit OTDR, find the length of that cable and go. There's an automatic setup of some of the key test parameters, selection of your network type, PON or point-to-point, etc. for your networks. The ability to define launch and receiver fiber settings. We'll talk about that in a little bit. The ability to set up and apply thresholds for measurements. Most OTDRs today come with an industry standard set of pass-fail thresholds. These can be adjusted by the users, and with all of the OTDR customers we have and all the units we sell, I would say less than 1% are actually changing these default values. We're actually working with a customer right now that actually wants to do that because they're seeing in their network design, there's some reflections that are a bit too much for industry standards. So you can set those up, save those as a profile to be used in the future. Trace and link maps are based on single pulse measurements in the easy OTDR. Again, you're not really using the easy mode to dig into or interrogate a fiber that you're questioning, but typically this is used for outage environments. The link map mode is a full auto mode with multi-pulse acquisition. So this will do multiple shots with different pulse widths. So it automatically sets up the parameters, select your network type, again, define the launch and receive fiber settings. You can do the thresholds, and the link map will be based on these multi-pulse measurements. And this is going to be just a link map view, so you're not going to see the trace. And then there's expert OTDR. So if you're dealing with fibers that are questionable, you want your most proficient fiber guy to work on that and give him full access to the setup of the OTDR. So you can set manual or auto mode and set all the same parameters. If you're doing a tunable, you can set up the grid, etc. So they have access to all of this stuff, and the end results are going to be the same. You're going to have a trace, you're going to have a link map, you're going to have events, you're going to look at that stuff. But it's just how you get there and who's using the OTDR for what purposes are the selections of the different modes. And again, all vendors of OTDRs have these different modes, and we all kind of will preach the same guidance as far as when to use which of the modes. Again, the full auto mode, really not a whole lot of setup. You can go through, select your wavelengths, select your type of fiber, and then you can run your test. The test parameters, if you don't, in an outage environment, you're not really worried about parameters, pass and fail, etc. But you do want to get your network type correct, if it's a PON, not a PON, etc. The trace and link map will be based on a single pulse, as I mentioned before. The other parameters, again, thresholds in an easy mode, you don't really need to worry about that. There's something called a front panel check, which is a connector check of the OTDR connection. It'll look at that for loss and reflection. If that port gets dirty, that port gets a lot of use. If you're using an OTDR every day, that connection on the top of the OTDR, side of the OTDR, etc., needs to be clean, needs to be scoped to make sure it's contaminant and reflection free. So we put a checkbox in there. You can skip that. I recommend leave it on the whole time. It's very important to have that connector to be clean because it can deter or deviate from your actual results and cause inaccuracies. And the last thing you want to do is be inaccurate with where you want to go look for a problem. Down below, there's something called span. So what span is, you can set up a launch fiber. And what a launch fiber is, and again, we'll go into this a little bit more later, is a reel of fiber that sits between the OTDR and the fiber you're testing, okay? When an OTDR launches, there's going to be a dead zone, launch dead zone. OTDRs nowadays have gotten this dead zone down to very, very little to where a lot of times you don't even need a launch cable. But there are cases where you want to use that. If you're up against a MUX and you want to just shoot channel back or a splitter, you want to make sure you have a reel in there. So if there's any events that are close to the point of connection, you don't want to jump over them. If you've used a coax TDR, it's the same principle. A twisted pair TDR, the same principle. If you're jumping over any events, you don't want to do that. So the span can be set inside there, and you can measure your reel. You can just look at the distance on the back of it. My recommendation is to measure the launch reel. When these are assembled, they could be a little bit different. They're really not going to be much, but you never know. It's always safer to measure it and use whatever measurement that is as event one. And then you can, that gets included into the overall length of your test. Again, the folks last night I was working with were not accounting for that, so they were a little bit off in their distances. So the link map has vendor-specific naming conventions. So basically, you'll have that map there, and there's some default test scripts in there that you can make use of. You can also create your own as well. The link map, again, the setup is going to look the same. Pick your wavelengths, etc., and you will do your test. The only difference here is when your test finishes, you're only going to have access to the link map. And a lot of companies have moved to this map-only environment as to not confuse the techs. And, there's more and more pressure out there on the technician to either fix an outage, repair a trouble, etc. And simplifying the whole OTDR process just relieves them of another headache. They got enough to worry about. They want to get their information, figure out where the problem is, and go fix it. Then in the expert mode, there's all sorts of things that you can set, okay, in addition to the fiber types and their wavelengths, etc. But in this mode, you have access to all of this. And again, this would be for the more proficient users. Even the proficient user, he may go out and do an auto just to find the end of the fiber. And if it's 40,000 feet, it's okay, that looks about right. Then you can switch to the expert mode and go in and set your distance, set your pulse widths, etc., and really dig into that fiber and see if there's anything going on in there that shouldn't be, needs to be addressed. Question number 1, Woody, here we go.
Okay, give me just a second. I'll get it up here. So audience, be on the lookout on your screen for a question. Pop up here in just a second. Okay, so I put up the question. Let me see if I need to do anything else. Polling in progress. So, okay, we're collecting responses. So question is, what fiber optic network types can the OTDR be used on? Point-to-point, C, or DWDM, MUX, PON, or all the above? So I'll go on mute. We'll give that a second. And also, we have another question. I will ask Pete while we were taken care of this. So the question is from Jacob Sindel. Will the this be available at a later date? Yes, the presentation will be available at a later date. So in case you're not aware, what you do to get to previous presentations is you go back into the events calendar on the scte.org website, and you look at that, you find the date of the event, and in that, when you open it up, you will see a link that will replay the webinar for you. So we've made it a little easier for you, and hopefully that answers your question and you'll get a chance to view it. And again, hopefully others that have missed this will also get a chance to view it. Let's see where we are in the poll. 49% voted, so we'll just give it another minute here. Looks like that has stalled, so let me show the results. We're up to 54%. Somebody else, last second, guys, if you want, ladies and gentlemen, in case you want to vote, if you get up to 55%. So I'm going to close it now. We're going to look at the results. Share. Okay. Here we go. Looks like everybody got it right. So 98%, all of the above. Thank you everybody for participating.
Excellent. Nope, it was not a trick question. All right. On we go. Additional expert OTDR test parameters. So this is where you can get into customizing the setup of your OTDR. Okay. Fiber characterization is usually performed at wavelengths corresponding to the system's operating range. So this is a key. If you're dealing with legacy telco networks, CWDM networks, DW networks, PON, etc., you want to test at the wavelengths that will be carrying traffic. So it's very important to match, what wavelengths are going to be used. Multi-mode for data centers, school systems, office buildings, small campuses, etc., lands 850 or 1300 nanometers. These are your multi-mode wavelengths. Single mode data centers, these larger data centers getting larger and larger as we speak. Legacy telecom networks, 1310, 1550, or 1310, 1550, 1625. These are also going to be your transport networks, legacy transport networks, etc. GPON networks, 1310, 1490, 1550. PON optimized OTDRs will have additional wavelengths as well. CWDM systems, this is governed by ITU G.692.1. So there's 20 nanometer intervals between those wavelengths. So you want to use CWDM based wavelengths in your OTDR. DWDM, C-band and L-band systems. This is ITU G.694.1. And this is flexible. So within the DWDM C and L bands, there's various channel spacings that you can use. And in the access world, whether it's fiber nodes, hubs, etc., typically we're at 100 gigahertz spacing. Okay? There's also 200 gigahertz spacing, 50 gigahertz spacing, and even some lower than that. As you can imagine, the 200 gigahertz spacing systems, the electronics for the transport systems are a little bit more cost effective because you don't have as many channels potentially on the fiber. You get into 100 gigahertz, there's more channels. Get into 50 gigahertz, there's twice as many channels as the 100. So while you can fit more traffic in there, the transport equipment, the electronics at both ends will go up in price accordingly. And that's just a factor of the electronics being more complex, carrying higher loads, higher capacities, etc. In-service testing and monitoring, 1625 nanometers or 1650 on the single mode side. These will not disrupt existing traffic that rides on lower wavelengths. Now, this is the second time I've mentioned monitoring in here. So there are systems out there that every vendor produces and deploys that can monitor your fibers 24/7. So these are very complex systems as far as what they do, but often they're very simple as far as what the monitoring user interface looks like. So basically, instead of routing your fibers out of the transmitters to the outside plant fibers, they go into a switch first before they go to the outside world. In that switch, the OTDR signal is laid on top of each of those ports. And the OTDR will monitor and shoot at those out of range wavelengths all day, all night, every day. And when there's a problem, it will tell you whether the network degraded, you have more loss, worse reflections, you have breaks. These are tied into mapping systems and the knock, etc. And when there's an outage, you know exactly where the outage is. You don't have to send a guy to the head end of the hub to do a shot, because the fiber system will tell you in the form of a knock notification, a trap, a push notification, an email, etc. And that drastically reduces your mean time to repair. These systems were very, very popular in Europe for years, and they're now starting to be very popular in the US to kind of speed up that repair time when there's an outage. But very important to use the proper wavelengths when you're dealing with OTDRs. Rapid fire succession. Audience poll question number 2, Woody. Go ahead. Did that one come up on your end, Woody? There we go. And Woody, let me know when you're good to go, because I can't hear. I don't have any audio now for some reason.
Hey, Pete, can you hear me now?
Yes, sir.
Okay. I can hear you too.
How'd we do on that poll?
So the poll is down. You can move forward. 81%
All right.
of people got it right, which is yes, you can perform OTDR testing with traffic on the fiber.
Excellent, excellent. All right, here we go. Additional OTDR test parameters in the expert mode, the distance settings. So this is an important piece so you get a usable, workable trace on the screen. So in the manual test mode, if the fiber length is known, the user can opt to set the range manually in metric or imperial units, the various types of settings there. The auto test mode that will configure the fiber length, which is set to distance range automatically. So this, if you don't know the range, you have an outage, etc., you can just use the auto mode and go. There's also some auto zoom settings that automatically scales the trace to optimize the display, the viewing area when this selection is enabled. And this is helpful to minimize navigation, etc. So the pulse repetition rate is set by the range setting, and this is just the pulse continuously being sent out at a specific duration in time. Always ensure the distance range is set to at least 1.2 times of the fiber length under test to avoid ghosting. This is a common question we get from the field when folks call in. When I'm not doing things like this or out with customers doing testing, training, etc., I join the tech support group and we field phone calls. And one of them that often comes in and say, hey, I'm not seeing the end of the fiber, I don't know what this display looks like, etc. So these examples down below here, the one on the left, the range is set too short. So if you manually set the range and you do your test, you won't see the entire link. So you'd be like, what am I looking at? In the middle picture, the fiber range is set too far. So if you set a long range in there and your fiber is fairly short, you're going to get a very compressed trace. So it will be all crammed into the left side of the screen as we see below. The third example in the middle there, the range set correctly. So you basically want to use as much of the display screen, much of that real estate as possible. So when we talk about setting the minimum to 1.2 times the length of the fiber, you will clearly see the end of the fiber. This will also minimize the chance of that end reflection having an adverse effect on the distance declaration. So what happens is when a fiber gets cut or ripped or the pole gets knocked down, that now becomes a fiber that has a very non-clean end face. So there could be different types of reflections coming out of there, and it could, if it's close enough to the actual end setting in the OTDR, it could disrupt your measurement. So going a little bit higher is what's going to be recommended. And what you'll see in a lot of OTDRs, and ours, our lab for our optical tools is in Europe. So everything defaults to kilometers, etc. And when you have your drop-down settings for your distance, you have 1 kilometer, 5 kilometers, 10, etc. And they're nice and normal, clean values. But when you convert to feet, there's some oddballs in there because it's just the conversion from kilometers or whatever the metric is into feet, miles, kilofeet, etc. So just be aware of that there. The pulse width. I mentioned this a couple times over the course of the presentation. And the pulse width basically will control the amount of light injected into the fiber. Shorter pulse widths have less dynamic range as far, but are used on short fibers to optimize the resolution in dead zones. So that the smaller pulse will give you a bit more resolution into what's in that fiber. Longer pulse widths have less resolution, but should be used on longer fibers when more dynamic range is required. In the manual test mode, in some situations, you can set and play with those pulse widths to get the view that you want to view. In the auto test mode, the pulse will be configured automatically to optimize the range, because we're just really looking for distance. The samples at the bottom here, if the pulse is too narrow, you can't see the entire link because it may not get you as far, and also the backscatter may cause it to disappear into the noise. If the pulse is too wide, poor resolution, which means you could miss events close to the OTDR or after following a dead zone. The pulse is set correctly. So each of these little OTDR traces at the bottom here is shot on the same fiber. And it's been simplified to really prove a couple of points here. So the one on the left where the pulse is too narrow, you have some noise in that trace and you have a little bit of a drop at the end there. In the middle, the pulse is too wide, so you're just seeing the beginning and the end of the fiber. And in the third example, towards the middle of the screen there, the fiber length, the pulse is correct because we see the beginning of the fiber, an event in the middle, and then the end of the fiber. This is also helpful when you have events that are very, very close together. We get a lot of questions on, we do training specifically. The folks will always, let's test this OTDR or test this fiber and see what the OTDR has to say. And we did a couple of months ago, I was at a customer and we shot the fiber and it was basically feeding a bunch of HFC nodes. And they were saying that there's an event that it wasn't detecting. And it's like, okay, let's lower the pulse width a little bit. So we dropped the pulse width down and said, now we can see the two events very, very close to each other. And if we used a larger pulse, it skipped over it. It flagged one, but not both. This is a case where the larger pulse with less resolution will skip an event. So if you have a known fiber link, what the makeup is, you can adjust your OTDR to the proper settings, specifically with the pulse, to identify all of those events that are there. So there's some various pulse width settings in your OTDR. Our OTDRs over the past several years, we've reduced the available pulse width settings per the distance. So if I select a short distance for my OTDR, I will not see the much larger pulse width settings that would totally blow my measurement out of the water. I'll see the beginning and the end of fiber, but maybe the 10, 12 events in between because I'm using a pulse width that's way too long. So this is helpful to the technicians in the field and reduces mistakes and bad or inaccurate OTDR traces. Averaging time. So this is basically the length of time that the OTDR will run, gather its information before putting a trace and/or link map on the screen. The OTDR will transmit these light pulses repetitively into the fiber, and it averages all of the results of each pulse. Averaging takes some time, but after a while, enough data will have been sampled to yield good results. If you're dealing with an outage, you can do a 5-10 second shot, doesn't really matter. If you're dealing with a link that you want to interrogate to compare it to design, see if there's any additional events there that are causing problems, you want to increase the length of time, you want to let that run. So the averaging time will improve the dynamic range and also smooth out noisy traces without sacrificing the resolution or adding to dead zones. So it's not a big deal to let it run longer. The manual test mode, you can choose fixed averaging times ranging from 10 seconds to 10 minutes. Auto test modes typically will start at a minute. If you're doing multiple wavelengths, it may do 30 seconds per wavelength, still totaling a minute, but this will configure the averaging time automatically based on the range and the resolution. In the live test mode, the average data is collected continuously until the measurement is stopped by the user. This can also be called real-time mode or all-time mode, whatever terminology you want to use. Basically, you turn it on, the OTDR will run until you hit stop. This is also handy for If there's a guy out in the field and you want to identify a fiber, you can put a microbend in there and see if it shows up, kind of like toning out cables, if you will. Also, proficient or veteran users of an OTDR. I have a friend of mine that does construction for power companies, and they'll do a lot of point-to-point, data center to a substation, et cetera, and they'll put a 12-count fiber in. He'll put his OTDR in real-time or live test mode, plug it into port 1, look at it, move it to port 2, look at it. He just has a trained eye, and there's a lot of guys out there like that they just need to figure out if all the fibers are the same, and they can do that very, very quickly because they've been doing it for many, many years. So our examples on the bottom, our fiber link, the makeup is the same, and our example on the left, the averaging time is too short. So the trace appears very noisy, and the noise floor ends up being a little bit higher. In the middle there, the averaging time is too much, and the trace is smooth, but the extra time shows no noise improvement. It's just a time saver there. And then the averaging time set correctly, we can see all the events. We have the downward trace, and there's no noise there. Less testing time. Testing times can be, people will consider that splitting hairs, but if you do this many, many times a day, it ends up, if you can save yourself a little bit of time based on experience, you can be more productive. Distance and resolution. So sampling resolution, this is an important factor in giving you greater detail into the fiber. How close the data points are spaced apart in time and distance. Distance accuracy is dependent on the sampling point spacing. This is basically resolution that you really don't see, but you will have sampling modes. In the auto, it'll optimize the resolution based on distance, pulse width, and test time. In the high sampling mode, uses the highest sampling rate for the best distance accuracy. Medium, it optimizes the sampling rate based on distance and test time. And then low, optimize the sampling rate based on distance only. So you can get a finer tooth comb by using the high sampling modes. So you can get greater analysis and detection of events that may be close together. When you get into muxes and splitters and cabinets, you may have multiple connections that are very close together, or you have splices right on the back of these. Seeing some changes in some of the pond architectures where a splice case may end up very, very close to a splitter, and when you shoot that with an OTDR, you may not see both events. So you can play around with these and experiment a little bit to figure out what the best settings are. And once you come up with a set of settings that you're happy with, you can save these as profiles to be used in the future, so you don't have to go through the setup each time. It's the same thing if you have an RF meter with spectrum analyzer settings, if you have an Ethernet test set with certain kinds of test setups. You want to make your life easier by arriving at a test mode that you like, save it as a profile for easy access in the future. Dead zones. So dead zones and dynamic ranges come into play as far as using the OTDR and also interpreting what your trace looks like. So a dead zone mode will adjust the OTDR receiver bandwidth to work with as small a dead zone as possible. And the dead zones are going to be your launch and also after each event and during attenuation. Higher noise floors are going to deal with, you're going to deal with when there's older fibers, mechanical connections, etc., or a lot of loss in there. The dynamic range mode will adjust the OTDR receiver to optimize the dynamic range for distance, etc. Okay, we get a lot of questions. How far can the OTDR shoot? Well, it's not a matter of how far can it shoot, but what is the dynamic range? What is the overall loss budget of the link you're looking to test? So the OTDR will come in a dynamic range per wavelength. So at 1310, you may have a 39 dB. If that link under test is way less than 39 dB overall attenuation, or the link budget there, you can reach the end of the fiber. Dynamic range is important to be able to withstand, as you go up in dynamic range, the cost of the OTDR will go up. So your local units, your campus units, etc., they're going to be very, very inexpensive. Your last mile PON, etc. But if you get into long distance, higher end OTDRs with bigger dynamic ranges, such as we deal with in the Caribbean, with Alaska, with Hawaii, there's a lot of long range fibers that you need higher dynamic range OTDR. And then there's automatic dynamic range in dead zone mode, and that optimizes for both. And truthfully, most people leave it in the automatic DR DZ mode, so they don't have to tweak anything or if they're concerned with it. Index of refraction settings. This value must be set correctly or the OTDR will either overestimate or underestimate the fiber length. This is very similar to the velocity of propagation in a coax TDR. The same principle applies, that you have the correct vendor's index of refraction based on the fiber model menu. And typically there's a selection or a drop down that has these models in it. If you want, you can look at any vendor, fiber optic cable vendors' websites to get their settings. In our case, in VeEX's case, we've greatly added to fiber models over the years. And most of the time, this is driven by customers' requests. Very easy to just add another type of fiber in there so they can pick that from a drop down. So some of the fiber facts: longer wavelengths travel faster through the core of the fiber, so the index of refraction values are different compared to shorter wavelengths. So if you looked in the system, there's settings for the different wavelengths, etc., but that's covered in each of the type of drop downs there. This one is a Corning that was showing the index of refraction for 1310 and 1550. And that is all rolled into that drop down. So you don't have to worry about the specific wavelengths. If you know the type of fiber that's out there, pick it and you should be fine. Some specifications, dynamic range. I started to talk before about how far can the OTDR measure. Okay, so this is just some quick explanations. One-way fiber loss, dB, from the backscatter level to the given signal to noise ratio on the trace. And this is just basically, can we make it from point A to point B before we have too much backscatter or our signal to noise drops down to where we can't see the other end. So this is determined by a combination of the total laser power and the sensitivity of the detector, including the electronics in the OTDR. So this will determine the approximate length of the fiber that we can measure. Again, the common question from a prospective customer: hey, how far can this OTDR shoot? And then you have to get into, what type of lengths are you dealing with? Are you dealing with PON that has more attenuation, etc.? The industry standards. Most of this was driven by Bellcore. If you guys are old like me and remember Bellcore back in the day, that later became Telcordia when the Bell system was dismantled. And they kind of drive this with their GR196, and there's some averaging time recommendations, etc., for a good indicator of the OTDR's usable measurement. And this is where it gets into the mathematics and things, and all the OTDR vendors take this kind of stuff into consideration when they are developing their tools. So again, it all goes back to the SOR Bellcore Telcordia standard, which keeps all the vendors pretty common as far as their capabilities. So dead zones, definitions as far as these dead zones, where the OTDR is unable to measure or locate an event following a reflection. So it's basically a blind spot. So up in here, those couple examples there, the top example has a very small dead zone, which means if there was an event that was very close, you're more likely to detect it. The bottom example, the dead zone, is much larger. It could be a higher pulse width there, and you can skip over an event that may be close together. This is real important for you guys that deal with muxes. When muxes start to go bad, you end up seeing multiple reflections inside the mux. So that would be an indicator of the mux might be on its way out. So you want to experiment and use different pulse widths to kind of give you a little bit more resolution to maybe just prove that there's nothing inside of that mux. Event dead zones, when there's an event along the way, There will be a little dead zone beyond that. And these are very, very small nowadays. So the event dead zone is also related to the pulse width setting. So in here, higher pulse width will give you a larger dead zone, and also the connectors and things, if you have a connection, manual connection between different parts of the fiber, such as office buildings and campuses where there's a lot of patches that take place. More and more stuff is becoming spliced, so there's a lot less of event dead zones that really take place. A splice really isn't going to give you anything if it's detected at all. Attenuation dead zone, this is the minimum distance after a reflective event, where a non-reflective event can be measured to within plus or minus half a dB of accuracy. So this has to do with how much loss. If you're using the OTDR to measure loss at each event during the link, if you're concerned with that, you want to be as accurate as possible. In a lot of the networks, there's enough headroom where you don't have to be down to a half a dB of accuracy. But there are cases where service providers are pushing the limits of their network, and every part of a dB that they can gain or pull out of that network is needed. So attenuation dead zone definitely has something to do with the pulse width setting, and the dead zone also is related to the connectors and finish. So if there's connectors along the way, you want to make sure that those are clean and well secured. Back reflection, so this gets into a little bit more about connectors polish and the impact that they have on the reflections and the performance. So many connectors have been used over the years. Flat polish has zero dome shaped geometry. So this is basically a flat, and it's going to give you the most reflection of any of the connectors. You know, in the old telco days that I was a part of, this is all we had in our central offices and facility sites. Physical contact polish, or the PC, was a little bit of a dome shape, so it gives you a little bit of a better core area contact and slightly less reflection back. Then there became UPC, which is a little bit more dome shape, and enhanced the polishing a little bit to optimize the connector and the core area contact. So these have a little bit more pressure between the two end faces. And there's several grades of polishing that were experimented with and arrived at and deployed to optimize that connection, if you will. With those two, those three actually, there is direct reflections that will go back towards the transmitter. Okay. And if you guys have RF in the background, you want to minimize that reflected signal back, because it can affect the forward signal that's coming down the pipe there. Enter the angled physical contact polish, or APC. That will redirect the reflection out of the interface. Okay. What will happen is the 8-degree angle causes the reflection to exit the core and dissipate into the cladding. And this is what you want. You don't want any of that signal to be reflected back to affect your forward transmission. So as far as the reflections, the boundaries here, glass to air, those couple at the top there, neg 14, not a very good reflection. PC to PC connectors, a little bit better. Okay, you're going to improve on that, neg 35 to neg 50. APC to APC, neg 55 to neg 65. These are ultimates. So this is what you want to see as far as the connections there. And if you have old connections in the plant, you need to be aware of this. Most cable providers, over the last, I want to say 10 plus years, 15 plus years, maybe even longer, have been using APCs. They were much faster to adopt that than the traditional phone companies did, because when the phone companies had been doing this many, many years ago, and there was nothing else available. Now they're at a point where you just can't change the stuff that's already deployed, because it will be an astronomical expense, and there will be outage, etc., downtime, and nobody wants that. Some more measurements. Auto trace analysis. Okay, after the trace is made, you can get a pretty good analysis here as far as whether your technician is very skilled or not. Beginning of fiber, end of fiber, etc. The events are presented in an intuitive table, allowing easy interpretation. I want to probably take this one out of here eventually, because with the transition to link map, the events tables are, a little bit much more difficult to read than the link map is. So in all sorts of navigation, events can be centered, zoomed automatically, etc., manually, and the table can be hidden or have it visible if you need more space on the screen. Separate events table for each wavelength is also possible. Link maps. Talked a little bit about this earlier. The iconic representation of the trace and events. So if you look at these side by side here, or top to bottom, the link map is much easier than looking at the trace to determine what's there. Consistent fiber analysis, regardless of the technician's skill level. Again, you can send almost anyone out to an outage, or to even look at a fiber, and they can look at the events that are presented in the link map, and it's much more intuitive for them as well. The link map will contain current and total information, which means you can click on an event to see exactly what that particular event is measured, whether it's got loss, reflection, etc., and then a summary of the entire link. And then you can also add, delete, or change these if needed. The detection process, no matter what OTDR vendor you are, is not 100% science. It's 99%, etc. And on occasion, the OTDR can be tricked into claiming this is a connector versus etc., split, splice, etc. So you can actually change those if you need to. If you're doing it in a construction job and you need to install per a design, you can change the icons to do that. Again, that's a tedious process, and it almost never happens, but the capability is there if there's a steadfast customer that wants to see that. Why link mapping? This basically is being driven by a number of things. More and more networks are changing from copper to fiber. People want to make it easier for the technician to take a look at that fiber. The technician skill set, lack of fiber expertise, just makes life easier. Competitor solutions, all the vendors do the maps now. This started many, many years ago, and it's been adopted by anyone who uses OTDRs. It's not just cable companies, phone companies, anybody who has fiber, campuses, the big pharmaceutical complexes, car dealers, or manufacturers, etc., military, government, all of those. So the easier it can be, the better. So the link mapping has been pushed everywhere. Testing challenges, setting the optimal test parameters for fiber testing is very difficult for novices. The auto modes are very, very helpful. In the map modes, the vScout modes, whatever you want to call them, there's many existing setups that the technician can use based on the topology of the network. Identifying dependent fiber problems, macro bends, etc. Again, these use multiple pulse widths, multiple wavelengths. The technician has to start the test once, and it will run all of these different things to do a deeper dive into that fiber. So along with that link map came this automated sequence of tests, if you will. So it can combine all this test data from all of these into a single display format. Correct OTDR trace interpretation and analysis requires a certain level of fiber expertise or intensive training. The link map will make most technicians much more proficient in dealing with the fiber. You don't have to deal with that trace. Is it a loss event? What's the reflection? Everything is there for you. So our solution is called vScout. It's the tool that creates the link map. But basically, as I said before, there's a bunch of scripted test setups in there for different kinds of networks that do all the work for you. Link map icons will identify problems and provides experienced technicians with simple repair advice. So if you look at these link maps that, it declares let's say it declared a splice, a connector. Well, that splice is either not good now or it went bad from the time it was done. So the loss characteristics of it exhibit more of a connector than a splice, and that would be addressed. So an experienced tech that knows what the network should look like will pick up on that and be able to say, hey, there's a problem at this distance. And the link map and the SOR file are both saved and embedded together in a PDF if you want to submit that to someone. Again, if I'm a contractor and I'm building a network for someone, every OTDR trace that I save, I can produce a PDF that has both the link map and the trace if I need to submit that for payment. So here's just another couple of samples of the link map along with a trace. So the traces can be a little difficult to look at. There's a couple traces here. The bottom one has got some good amount of events in it. So to navigate that screen and move around is a little bit of a challenge. Over on the left, there's an example of a link map. And the link map for the particular trace on the right, you have arrows where you can scroll back and forth and just look at each event. So it's a little bit more straightforward as far as from a technician standpoint, looking at that trace and saying, hey, I have 3 splices on the screen there at each of those distances. So it's much, much easier, and it provides all of that valuable information right there. The event table really isn't needed anymore because you have everything right in front of you, where that link map gives you everything that it finds along the way. So multiple wavelengths, again, I mentioned earlier, to find hidden impairments on suspect fibers. So this is where your customer is in service, but he's got intermittent problems and you want to rule out anything in fiber. So again, the link map with those predetermined scripts is your key to doing that in a very easy manner. Loss and markers. Some OTDRs, most OTDRs have the capability to use multiple markers. If you just want to zoom around a couple of events, see how far they are apart, how much loss is in between them, you can do that. So there's all sorts of navigation that you can do. Look at splices, connectors, etc., just to verify that the distances and where those events are, the loss values between the 2 markers is there. And if you are looking for specific parameters, they will give you the location of where each marker is, what the loss is between them, what the distance is between them, so you can manually manipulate all of these different points along the trace. Audience poll question number 3. Go ahead, Woody.
All right, hang on just a second. Here we go. So what advantages are realized when selecting multiple wavelengths when available to run an OTDR test? So we have can shoot further, identify types of fiber, locate harder to detect events, determine upstream issues. So we got a few people already voting. Let's I'm going to go on mute and give it a minute, and we'll review the answers. Last call for anyone to vote on this. Okay, we're going to go ahead and close the voting and share the results. Okay, so it looks like we had 91% said locate harder to detect events. So I believe that is correct, right, Pete?
That is correct, absolutely.
Yeah, so it looks like our audience know a little bit about TDRs, are learning quickly. So thank you, Pete. I'll close this and we'll move on.
All right. Cool. Other measurements called least squares approximation. This is a method that will kind of zero in on splices and give you information about the splices, loss, etc. And like I said, splicing has improved to the point where most people don't even look at this anymore. Splices, if they are detected, are very, very low attenuation values, and the OTDR still can look at these, but not many people are even looking at this anymore because the splicing has just gotten so much better. Reflections. So the ratio of reflected power to incident power expressed in a negative dB value. Okay, over to the right, our little reminder guy up there, PC connector, neg 45, UPC, neg 55, APC, neg 65. Again, for each event, the higher the negative number, the better. So neg 65 is better than neg 55. Okay, so the worse the connection, the higher reflection, and the light reflected back to the source. Bad reflections can cause unwanted echoes in the fiber, resulting in bit errors and higher bit error rates. As you go up in bandwidth, okay, I don't know the scope of the audience. We've been selling a lot of 100 gigabit Ethernet equipment for the past bunch of years. We've ramped up 400 gig Ethernet test equipment. Now we're rolling out 800 gig test equipment. Reflections are very, very critical in these higher bandwidth applications. Okay, the same thing goes for power levels, etc. So you don't want very large reflections along the way. If you have a large reflection that's picked up by an OTDR, you want to investigate that. What is that event? Is it some kind of connector? Hopefully it's not a splice, but you always want to make sure that your reflections can be minimized. That's a very key component for high rate transmission networks. Overall return loss. So this is a computation combining the reflections of all the events along the way. So it's a logarithmic ratio of the incident power and the reflected power in the fiber system. Little formula there. So the OTDR will take all of those measurements and combine those. The reflected power, the total amount of light reflected back to the OTDR by the fiber. And this has to do with that Rayleigh scattering and the components along the way. And these components are all the connections, splices, ends of fiber, whatever. High ORL values, the better. So this is reflected in a positive number. Okay, so the higher the better. Okay, this is often a service level agreement for fiber providers. For example, Verizon Wireless is very big on this. If someone is providing the fiber transport for them, they will require an OTDR shot that includes the length, the overall attenuation, and an ORL measurement as well. A few years ago, they were, I think a minimum was like 28, 29. Now I think they're 34, 35, something like that. That may be another provider too, but the higher the number, the better. So if you're a service provider and you have somebody providing dark fiber for you, you want a higher, more stringent ORL value. So the OTDR and the PC analysis software can be used to measure section and total length. So if you have a problem in part of your fiber, any PC analysis software that is compatible with SOR traces, you can do a little bit of further analysis in there. And again, this is becoming less and less common, basically because of workmanship. You don't really have a lot of these issues anymore in these new builds. What is an OTDR SOR file? So this file that's created is a standard OTDR record, and it's a file system used to store the trace data in a standardized format. So the history of this SOR file, this was initially defined by Bellcore in 1995 to ensure compatibility between different OTDR vendors' trace data. Revised again in later than that, 2010, accommodate handhelds. As OTDRs changed, there were some slight changes made in the standards. It revised again in 2011 with different data formats, compatibilities, and different things, some backward compatibility. So overall, much like Cable Labs governs a lot of the RF parameters and DOCSIS parameter specs, Bellcore Telcordia did that on the phone company side. So Bellcore was a research arm, if you will, of the Bell companies when they were in existence. So these building blocks, they map, this is internal file makeup, if you will. These are all parts of what goes into that file. So the OTDR will produce this OTDR trace, and it's basically a result that you export from the OTDR, and you can put it into a PC or a cloud-based analyzer to look at the trace, look at events, etc. So instead of looking at the trace in the OTDR, you put the file into your computer or into the cloud, and you can look at it. And this was the way for many years of identifying OTDR. So if a guy out in the field did a trace, the trace would be exported and sent it to the guy who's the expert, the engineer, and he could determine what each event is, et cetera, whether it's good or bad. Now with all the advances, we barely ever have to export these SOR files. Most of the time, if I'm a contractor or a construction guy and I build a network, I can save the result, export a PDF, and I give it to whoever it needs to go to. I can still export the SOR, but it's becoming less common. OTDR accessories, some useful add-ons. I talked a little bit earlier about launch reels. Also, there's something called the receive fiber. This enables the tech to measure near and far end events of a fiber link. So if the fiber has events that are very, very close to the beginning where the OTDR is connected, you could miss those potentially. If it's a long fiber and you may miss an event that's 100 feet away, you can use a launch reel to extend yourself away from those events. So they come in all sorts of lengths, and that will fit between the OTDR and the fiber under test. All OTDRs have built-in launch, not all, but several have built-in launch fibers, very short. Typically, you don't generally have a lot of real estate inside your OTDR. Customers want smaller and smaller equipment, so you can't put a gigantic launch reel inside there. But there's all sorts of fiber launch reels that you can buy, and you can set what's called a span begin if you're using a launch reel between your OTDR and the fiber under test. But there's also something called a receive fiber or span end if you want to put a piece of fiber at the end of your link under test. Now, this is done for a couple different things. You may have a bad reflection at the end, so you want to put a connector there to accurately characterize that connection. In some cases, if your ORL is just on the edge of being acceptable to your customer, you might want to put a connector at the end to reduce that reflection a little bit and may help your overall reflection. But what will end up happening is your beginning of fiber will actually be, let's take 1 kilometer, for instance. Instead of your link under test being 39 kilometers, it's 40. But the OTDR will subtract that out and still give you the correct length. Other accessories, this is very, very important. Cleaning kits. Okay, anytime you open a fiber, you should clean it, inspect it, etc. We have a saying called CLICK, clean, inspect, connect. So various carrying kits or fiber cleaning kits are available on the market. There's a lot of vendors that sell them. OTDR vendors sell them, supply houses, etc. But you should have an assortment of cleaners there. You don't want to leave your fibers questionable. If you don't have a fiber scope, at least clean them when you connect them. Also, I mentioned that front panel check. You want to make sure that your connector on top of your OTDR is clean. Very easy to keep that clean with the one-clicks, with wipes, etc. You want to make sure that those, anytime the fiber is opened up, you want to clean it before you connect it to whether it's your tool or a patch panel, a node, etc. Fiber scopes. Why inspect fiber end faces? So this is something that's very simple, but very, very important because dirty connectors will impact optical performance. And again, as you go higher in bandwidth, 10 gig, 40 gig, 100 gig, 400 gig, etc., this dust is going to impair the contact between the connectors, creating small gaps, and can also actually permanently damage the end face. If you damage the end face on your OTDR, no matter whose it is, you can expect a decent repair bill. A lot of OTDR vendors, such as us, sell a little protector barrel or connector. Basically, plug that in, and then when that connector actually goes bad down the road, you can just replace it instead of risking damage to the OTDR connector. RF meters have saver barrels on them if the barrel is connected right to the board, but high insertion loss and reflections due to contamination are the #1 cause for fiber failures. Not just total outages, but intermittent performance. Total loss of signal is certainly a risk, and the recommended practices, connector inspection steps. Before connecting, clean the end face, both mated pairs. This also if you're plugging in a jumper to a patch panel, clean both connectors. Inspect each mated pair with a fibroscope. Contamination persists, re-clean and re-inspect until it's clean. Connect each connector immediately after successful visual inspection. You don't want to leave a fiber hanging, because any dust that's being blown around by all the fans that are usually near where you're working, you don't want dirt to be blown onto that fiber. And it happens pretty quick. Even if you're outside at a fiber cabinet, cross box or something, any little wind, any little bit of dirt's going to kick up. So you don't want to have that fiber laying open without a protector on it, dust cover, or plugged into its connector. Down below, there's some samples. The far left is a nice clean fiber connector. Wanted to also remind you that most fibroscopes now, for years now, have had a pass-fail template that's a IEC standard. So there's no, well, that fiber looks good. It'll tell you pass-fail right there. No gray areas. The next picture, moving from left to right, is alcohol residue. Also, touching contact with your skin. If you happen to have a fiber end face hit your skin, you'll get some residue on there. If you guys smoke nowadays, don't smoke around the open end fiber, because that cloud will actually get on there a little bit. Wiping it on your shirt or a random cloth, yes, you can actually clean it and pass it, but it's not recommended. You may get cloth fibers on there that will get in the way of your connection. Dust particles, also things like that, are detrimental to the connection. These are the audience questions. I've come to the end of my presentation. There's a QR code on there that you can scan with your phone. I'll leave that up there. That will get you to our website if you want to sign up to get a OTDR Basics poster. We'll mail you a little poster out that you can hang in one of your tech rooms or office, or etc.
And I am not seeing any more questions, so I just want to take a moment to thank Pete for this excellent presentation. And for those who might have missed some of it or want to get past the audio, well, I guess you can't get past the audio issues because we recorded this. But if you would like to see this again, be on the lookout in a week or two. It should be posted again on the events calendar, SCT events calendar, and it will be under the title. You'll see a link that will automatically start the replay if you click on it. So thank you everybody for joining. And just a note, before we close here, I did put the links in the chat for those who would like to nominate Member of the Year, also registration for Vendors Day and registration for Cable Games. So again, thank you, Pete, and thank the audience for everyone's attendance today. Yeah, everybody have a wonderful day. Thank you.
My pleasure, Woody. Take care, everyone. Have a good day.